Hi, this is Shelley Physics Linear Motion, practice E number 2. A flower pot falls from a windowsill 25 meters above the sidewalk. How fast is it moving when it strikes the ground, and how much time does a passerby have to get out of the way? Um, let's look at the problem solving uh, technique here. Write down and identify the given values, implied values, and unknown target. So the given value, there's only one. It might seem kind of strange here. I'm going to use Y this time, because this flower pot is falling. You can still use X if you want. Y is 25 meters. That's how far it's falling. It's going to go from the initial height of 25 down to the ground. So sometimes you might think about like where it's starting, where it's going. And letter A, how fast is the flower pot moving when it strikes the ground? So does that sound like a starting velocity or a final velocity? It's at the end. So when it strikes the ground is at the end. So that's a VF is our unknown. And we're also looking for the time that it takes to fall. That'd be how long it takes that passerby to get out of the way. So this is all we've got. Now looking at our equations of motion, we don't have a whole lot to go with here. You see there's a problem with VF that equals VO plus AT. So what do we do with that? We're looking for the VF, but we don't have an initial velocity, we don't have an acceleration, and we don't have the time. All we have is a y equals 25 meters. So we look down at the second equation. Remember x or y, they can be the same thing. Trying to get you to stretch out a little bit here and see that y and x, they're interchangeable, they're just the position. So the position, it's going to fall 25 meters. Is there an initial velocity? No, we don't have that. There's a time, acceleration, we don't have that. We look at the last one. The problem with the second equation is it doesn't have the final velocity. So what about the last one? Well, there we have an x. Oh, how about that? The distance it falls, that x can also be a y. But in order to find the final velocity there, we would need the initial velocity and the acceleration. You notice those two bits are missing. So do we know that? Is that implied? If a flower pot falls, what is the initial velocity? I have too many things showing up here. Okay, there we go. And problem solving test. There we go. So if an object falls, what's the velocity? It's zero. The initial velocity is zero if it's falling. It's not thrown downward. It's not chucked. It's not tossed. It just falls. So that is implied. The initial velocity is zero. Look for those zeros, especially with free fall problems. There's a couple of spots, a couple different places in an object's motion. If it's tossed up into the air, think about the velocity when it gets to the very tippy top point. And if an object's dropped or it falls like this flower pot, the initial velocity is zero. So do we also know the acceleration? Is that implied? Because that was one of our unknowns. Yes, acceleration due to gravity is 9.8 meters per second squared. So if it falls a distance of 25 meters and is accelerating at 9.8 meters per second squared, that's what's going to happen. We have all of our information now. Now, a couple things to note here. The y direction, I'm going to call down. It's going to fall down 25 meters. So does the 9.8 meters per second squared agree? Yeah, that's also down. Gravity is down. So because those are both in the same direction, let's consider that direction. We can call down positive. I'm going to call down my positive direction. So now any numbers that are positive are going to be in the down direction. So are we ready to go here? Equation set. Yes. Let's try out that third equation. Final velocity squared, I'm just going to rewrite it here, equals initial velocity squared plus 2a, and I'm using y instead of x. So I wrote it down. And let's look at our problem solving technique here. Number 2, check the list to be sure all units agree. If necessary, convert to standard units. I think we have all meters and seconds. I think we should add one more thing in number 2, and we already just looked at that. Consider the direction as well. Consider direction. And number 3, select the appropriate equation to use, write it down. And number 4, solve and consider, make sure it makes sense. Okay, so got the equation written down here. We're looking for the final velocity. So Vf squared equals the initial velocity squared plus 2 times acceleration times the y, and the y distance is 25 meters. All right, there it is. So let's do a little calculating here. There it is. And we're going to plug in 2 times 9.8 times, and we got 25 meters. That's 490. So I'll plug that in there. And our final velocity isn't 490 meters per second. It's the square root of that. I'll take the square root of both sides. And my square root is right here. So I got a 22.139, let's say 22.1 meters per second. That's it, or is it? Now we got one more part to it here. So let's bring up the time. We need to find the time. So we now have the final velocity, the initial velocity, the distance, the acceleration. So time should be rather easy. Let's bring up our equations. So the top two equations have time in them. We've got Vf equals Vo plus At, and x equals, in this case, y equals Vot plus half At squared. That second one is a little bit more involved. If you look at the first one, I do have all that information now. I've already solved for the final velocity. So I have the final velocity, the initial velocity, the acceleration, and I can solve for time. That's a good fit. So I'm going to use that one. I'll write it over here. Y equals, oops, not y equals, I'll write it down here. Vf equals Vo plus At. There it is. Our final velocity is 22.1, and the flower pot fell, so its initial velocity was 0. The acceleration is 9.8, and we're going to solve for time. So there's a 0 there. Just ignore that. Divide both sides by 9.8. Do our algebra, and I get a time of 22.1 divided by 9.8. Bring up the calculator again. 22.1 divided by 9.8 is 2.25, I'll say 2.26 seconds. There we go. That's all there is to that one.